So in this video, we'll continue our discussion of limits. You'll find the same set of notes in week 1. This is a continuation of the classroom discussion, so you'll find this in your class notes. We're going to talk about limits and infinity. Now, infinity is not a real number. Infinity is a concept. So the first rule, we're looking at the limit of x raised to the nth power as x approaches positive infinity. Now, what I mean by infinity is a concept, that means that x increases without bound. It's not a specific number. X increases without bound means that x becomes infinitely large. So if you look at this, for example, the limit of x to the nth as x approaches positive infinity is positive infinity. If you think about this, if you take a positive number and raise it to an odd power, then you're going to get a positive number back. Likewise, if you take a positive number and raise it to an even power, it's going to return a positive number. So if we take something which is infinitely large, in this case positive, and raise it to a power, then it will even become larger. If we take something infinitely large and it's positive, and we raise it to a power, then it even grows bigger. So the limit of x to the n as x approaches positive infinity will be positive infinity. It will increase without bound. Now, if we look at the limit of x to the n as x approaches negative infinity, and again, that means it decreases without bound, which means that it becomes infinitely negative. Well, this is a little bit more tricky, because if we take something which is negative and raise it to an even power, then the result is a positive. So if we take the limit of x squared as x approaches negative infinity, then that actually gives us positive infinity, because when we square a negative, that gives us a positive. The limit of x to the n as x approaches negative infinity is equal to negative infinity if n is odd. And again, that makes sense, because if you take a negative and raise it to an odd power, it will return a negative value. So the limit of x cubed as x approaches negative infinity would be negative infinity. Now, we're going to expand these concepts of the limit as x approaches positive or negative infinity to polynomial functions. And here, all we really need to do is look at the leading coefficient in the polynomial function. The leading coefficient is the term that has the greatest power of x. So if we're looking at the limit of negative 3x to the 4th plus 6x cubed minus 8x squared, then the leading coefficient here would be minus 3x to the 4th, because that is the one that has the greatest exponential power. So why do we only have to consider this? Well, think about it. If we're taking something which is infinitely large and raising it to the 4th power, it's going to become much greater than taking that same large value and raising it to the 3rd or 2nd power. So the leading coefficient here is going to dominate the value of that polynomial function. So here we are going to extend the previous rules, where we have taken a look at the limit of x to the n as x approaches either positive or negative infinity to polynomial functions. And a lot of these are common sense, so you may not necessarily have to memorize these. The limit of f of x as x approaches positive infinity is equal to the sign of that leading coefficient times positive infinity if n is even. And here n is even. So what happens when we take a really huge positive number and raise it to the fourth power? Well, it's still going to be positive, and it's even going to be greater, but since we're multiplying by a negative, then that's going to make the end result negative. So that's going to give us negative infinity. So basically what we're doing is, if n is even, which in this case is, and x is approaching positive infinity, that simply gives us whatever the sign of the leading coefficient is times infinity. So this is a negative sign, so that would be equal to minus infinity. And again, you don't necessarily need to memorize this because it just makes common sense. Again, a positive large number raised to an even power is still going to give us a positive quantity even greater. But when we attach the minus sign here, then it becomes negative infinity. Again, the leading coefficient in this particular polynomial is minus 3x to the fourth. And here, x approaches negative infinity. Now, again, if n is even, and we take a negative number, which is decreasing without bound, we take that negative value and we raise it to the fourth power, that gives us a positive. But if we attach the sign in front of the leading coefficient, then that will make that value negative. So the limit of f of x as x approaches negative infinity, if n is even, is equal to the sign of the leading coefficient times the infinity. Again, you can learn this rule if you like, but you can also just kind of think about it logically. Again, if we take a negative value and raise it to an even power, that gives us a positive, but the sign in front of this leading coefficient will make it negative. And again, we're not concerned with these other two terms in this polynomial function, because the value of this function is going to be dominated by the greatest power of x that appears in that polynomial function. If you take something which is infinitely large and raise it to the fourth power, it's going to get much greater than the same value raised to the third or second power. So again, it's the leading coefficient in these polynomial functions that are going to dominate the value of the polynomial function as x approaches infinity. And again, we have another rule, and here x is approaching positive infinity, and we're looking at the value of n being odd, and basically this one too is covered in is very much like rule number one, but we got to be careful and take into account the sign of the constant in the leading coefficient. And again, if we're talking about a value for x becoming infinitely large, increasing without bound, and it's positive, then if we cube that infinitely large value, that's going to give us a value which is even greater. And then to determine whether that quantity is going to be positive or negative, we have to look at the sign of the leading coefficient. So here it's positive, so that's going to give us positive infinity. The last rule in reference to the limits of polynomial functions as they approach either positive or negative infinity is where we have evaluating a polynomial function as x approaches negative infinity and n is odd. So again, here we have to take the opposite of the sign of the leading coefficient and attach an infinity to it. If we take a negative value which decreases without bound, that means x is approaching negative infinity, and we cube it, that gives us a negative value. You multiply it by 2, that gives us actually negative infinity here. That's an error there. It should be negative infinity, because what we're going to do is we're going to take opposite the sign of this value and attach an infinity to it. So that would be negative infinity. It should be negative infinity, not positive infinity. And again, the rule itself can be confusing, and that's why I just like to apply some common sense. Again, if you take a negative value which decreases without bound and raise it to an odd power, you're going to get a negative. You multiply it by 2, it's still going to give you a negative, so this will give you negative infinity. So let's just look at a couple of more. Suppose we have the limit of minus 3x to the 4th minus 6x squared plus 12 as x approaches negative infinity. And again, what I'm going to do is just use a common sense approach as opposed to trying to learn these 4 rules. So if we take a number that decreases without bound, that means it becomes infinitely negative, and we raise it to an even power, then that extreme negative value will become positive. And then when we multiply it times a negative, then it will become negative. So this is negative infinity. Again, this only works when you're evaluating polynomial functions at infinity. So in this case, the answer to this would be negative infinity. If we look at another one, say the limit of minus 5x squared plus 8x minus 10 as x approaches positive infinity. Again, this is your leading coefficient of your polynomial function, and it's pretty much going to dominate the value of this function. Because if you square something infinitely large, it becomes larger than if you take that same large number and multiply it by 8. So again, what I'm going to do is just use some common sense here. If we take a positive value and square it, it's still going to be positive, but it's even going to be greater. But when we multiply that by a negative, then that's going to give us a negative, so this is going to be negative infinity. The next thing we're going to talk about is left-hand and right-hand limits. And this is the greatest integer function, and I don't know if you're familiar with that or not, so let me explain what that is. F of x, or y, is equal to the greatest integer less than or equal to what's inside. So let's look at a couple of examples. Y is equal to the greatest integer less than or equal to what's inside here. So let's look at what happens around x equal to 2. So, for example, y, or f of x, would be, say, equal to the greatest integer less than or equal to what's inside. So suppose x was 1.5. Then the greatest integer less than or equal to 1.5 would be 1. So if x is equal to 1.5, then y would be equal to 1. Likewise, say y, or f of x, is equal to the greatest integer less than or equal to what's inside. Say what's inside is equal to 1.9. Well, the greatest integer less than or equal to 1.9, the greatest integer less than or equal to 1.9 would be 1. Remember, integers are consist of 0, the positive whole numbers, and their negatives. Well, so if x is equal to 1.9, y would be equal to 1. But now when we get on the other side of 2, say x is equal to 2.1. So this is the greatest integer function. This is what these brackets mean. And it means that y is the greatest integer less than or equal to what is inside here. So the greatest integer less than or equal to 2.1 would be 2. So when x is 2.1, then y is 2. And likewise, if f of x was equal to 2, the greatest integer less than or equal to what's inside would be 2. So when x is 2, y is 2. So here I say the limit as x approaches 2 does not exist, because as x approaches 2 from the left, okay, think about approaching 2 from the left here. That's what we're doing with these values here. As x approaches 2 from the left, that means x is a little bit less than 2. And the way we denote that is written like this. The limit as x approaches 2 from the left of the greatest integer function would be equal to 1. Now this is not a negative sign. If it were a negative sign, it would be in front of the 2 or to the left of 2. So if you see this notation and you have a little sign here that looks like a minus sign to the right of 2, that means that x is not quite 2. X is a little less than 2. In other words, you take 2 and you take a little bit away. You subtract a little bit from 2. So if the values for x are just a little less than 2, then the greatest integer less than or equal to what's inside would be 1. But if x approaches 2 from the right, as x approaches 2 from the right, here the values for x are approaching 2 from the right, that means that the values for x are a little bit greater than 2, and that's denoted, the limit, as x approaches 2 from the right. Now this is not a positive sign. If it were a positive sign, again, it would be written to the left of 2. That means that the values for x are a little bit greater than 2. Well, if the values for x are a little bit greater than 2, then the limit of x as x approaches 2 from the right would be equal to 2. For example, the greatest integer less than or equal to 2.1 is 2, so it gives you 2. The greatest integer less than or equal to 2.9 would be 2. So, again, this is what we call a right-hand limit. The limit as x approaches 2 from the right means that x is greater than 2. It's 2 plus a little bit, if you will. So this is called the greatest integer function. So in order for the ordinary limit to exist, the left and right limits must exist and be equal to each other. Well, here the left limit, that's the limit as x approaches 2 from the left, is equal to 1. It does exist. It is equal to 1. Here the limit as x approaches 2 from the right does exist, and it's equal to 2. But in order for the ordinary limit to exist, the left and right limits must both exist and be equal to each other. Well, here the left limit is equal to 1 and the right limit is equal to 2. So therefore we say that the ordinary limit, which is the limit as x approaches 2, does not exist. So in order for the ordinary limit to exist, then both the left and right limits must exist and be equal to each other. So here I'm asking you, does the ordinary limit of the square root of 9 minus x squared exist? So therefore what you have to do is you have to examine both the left and right limits. So the limit of x as x, the limit of f of x, which is the square root of 9 minus x squared, as x approaches 3 from the left. So that means that the values for x are a little bit less than 3, if you will. So they're sufficiently close to 3, but a little bit less than 3. So if you take a number which is close to 3, say 2.9 and square it, then that gives you a value which is a little bit less than 9. A little bit less than 9. So 9 minus a value which is a little bit less than 9 gives you the square root of a positive number, but it's going to be close to 0 because the closer we get to 3, but a little bit less than 3, the closer we're going to get a value when we square it close to 9. So that gives us 0. So the left hand limit does exist and is equal to 0. So now what we need to do is to look at the limit as x approaches 3 from the right. That means that values for x are going to be 3 plus a little bit. So they're going to be greater than 3. So we're taking the square root of 9 minus x squared. Now, if we take values which are a little bit greater than 3 and square them, then that's going to give us a value a little greater than 9. So we have 9 subtract a value which is a little greater than 9, which actually gives us a negative number. So we're taking the square root of a negative number. And that is an imaginary or complex number. We cannot take the square root of a negative number over the set of real numbers. So therefore, the limit of the quantity, the square root of 9 minus x squared, as x approaches 3 from the right, values for x are a little bit greater than 3, doesn't exist. Because this value here is imaginary. So the right limit doesn't exist. So since the right limit doesn't exist, the ordinary limit doesn't exist. So the answer to this question would be no. And again, this is not a negative value because it's to the right of 3. It means 3 less a little bit. So the values for x are a little less than 3. Excuse me. This is not a positive here. That means the values for x are a little bit greater than 3. 3 plus a little bit. And again, if we take a value greater than 3 and square it, then that gives us a number larger than 9. So when we subtract, that gives us the square root of a negative value, and that is imaginary. So the right limit doesn't exist. And in order for the ordinary limit to exist, both the left and right limits must exist and be equal to each other. Here, the left limit exists, but the right limit doesn't exist, so the ordinary limit doesn't exist as well. The last thing we're going to talk about is continuity and continuity of the point. And very briefly, just kind of let me review a couple of things. You can think of a function being continuous if you can graph that function without lifting your pencil. So this would be an example of a function that would be continuous. We've also graphed some piecewise functions. We did that in the first class, and that's when the graph of the function is in more than one piece. And we looked at, say, an example, and in this particular case, and this is, I think, one of the ones that we graphed the first night of class, this function is not continuous. It's not continuous because there's no way that you can graph this without lifting your pencil. So basically what we're looking at here is not necessarily the graph, but a definition of continuity using a limit. So a function is continuous at a point if, at a point x equal to a, if f of a is defined, if the limit of f of x as x approaches a exists. That means that both the left and right limits exist and are equal to each other. That both the left and right limits exist and are equal to each other. We just talked about what it means for the limit to exist. In order for the limit to exist, the left and right limits must exist and be equal to each other. And the third condition is that the ordinary limit must be equal to f of a. So to determine continuity at that point, you first of all have to make sure that f of a is defined, and then you have to look at both the left and right limits and see that they exist and are equal to each other, and then your ordinary limit should be equal to f of a. So here what I'm going to do is test this particular function for continuity. Now, if this function fails to be continuous, it is probably going to fail to be continuous around x equal to 0, because that's where the function does some crazy stuff. The function is equal to x squared plus 1 if x is not equal to 0. That means if x is either negative or positive, then this is the way we evaluate the function. We square x and add 1 to it. However, if x is equal to 0, then f of x simply becomes 2. So if this function is not continuous, then it will probably fail to be continuous around this particular value for x, because that's where the function does some funky things. So in order to determine whether this function is continuous at x equal to 0, then these three conditions must be defined, must be true. So the first thing I need to do is find f of a, and here f of a will be equal to f of 0. So what is the value of the function when x is equal to 0? The value of the function when x equal to 0 is 2. So f of 0 is 2. So the first condition of the definition of continuity is met. Now the second definition, or the second condition, is we have to look at the limit of the function as x approaches a. In this case, we're looking at the limit of the function as x approaches 0 from the left, and the limit of the function as x approaches 0 from the right. So we need to determine whether we're taking the limit of x squared plus 1 or the limit of 2. Well, what is f of x if x approaches 0 from the left? Well, if x approaches 0 from the left, that means that x is a little bit less than 0. If it's a little bit less than 0, then that means that the function takes on this value, x squared plus 1. And the limit of x squared plus 1 as x approaches 0 is equal to 1. Now again, we've got to determine if the ordinary limit exists. If the ordinary limit exists, then that means the left limit and the right limit must both exist and be equal to each other. When we found the left limit, now we need to find the right limit. So what does it mean for x to approach 0 from the right? That means the values for x are a little bit greater than 0. Well, if the values for x are a little greater than 0, then they're not equal to 0, so we're still evaluating this creature here, x squared plus 1. So the limit of x squared plus 1 as x approaches 0 from the right is still 1. Substitute 0 in for x. So the left and right limits both exist and are equal to each other. So that means that the ordinary limit exists because the left limit and the right limit both exist and are equal to each other. Now, the last condition we need to check is to determine if the ordinary limit here as x approaches a is equal to f of a. Well, the ordinary limit does exist. The ordinary limit is 1, and f of a is actually 2. And 1 is not equal to 2, so it fails to meet the third condition of our definition of continuity. So therefore, this function is not continuous at x equal to a. So we're still looking at continuity at a point. And in order for a function to be continuous at a point, then the following three conditions must be satisfied. F of a must be defined, the ordinary limit must exist, so that means the left and right limits must exist and be equal to each other, and the ordinary limit, this value, must be equal to this one. So we've looked at this example, so we're going to look at another example. Here, f of x is equal to x squared if x is less than 1, and it's equal to 2x if x is greater than or equal to 1. So we want to determine the continuity at x equal to 1. If this function fails to be continuous, it will probably fail to be continuous around x equal to 1, because that's where the function starts doing some funky things. X squared is equal to this, provided that x is less than 1, and f of x is equal to 2x, provided x is 1 or greater. And again, we're trying to determine if it's continuous at this point, not by looking at the graph, but looking at these three conditions. So the first thing we need to do is we need to determine if f of a exists. Now, a in this case is x equal to 1. So we need to find f of 1. So what is the value of this function when x is equal to 1? Well, if x is greater than or equal to 1, then f of x becomes 2x. So we need to find f of x, in this case f of 2x, so we're going to substitute 1 in for x in the function 2, and that gives us 2. So the function is defined at x equal to 1. It's equal to twice whatever the value of x is. So if x is equal to 1, then twice x would be equal to 2. The second thing we need to do is determine if the ordinary limit exists for f of x as x approaches 1. So in order for the ordinary limit to exist, both the left and right limits must exist. So we need to look at the limit of the function as x approaches 1 from the left, and we also need to look at the limit of the function f of x as x approaches 1 from the right. Alright, so this means that x is approaching 1 from the left, which means that the values for x will be 1, subtract a little bit. So it's a little bit less than 1. So when the values for x are a little less than 1, the function that we're evaluating is x squared. So this is the limit of x squared as x approaches 1 from the left. Alright, so this is the limit of x squared as x approaches 1 from the left. That means the values for x are a little bit less than 1. So when the values for x are a little bit less than 1, the function takes on the value x squared. So plugging 1 in for x here and evaluating the limit, we get 1 squared is 1. So the limit of the function as x approaches 1 from the left is equal to 1. Now, we need to evaluate the limit of the function as x approaches 1 from the right. Well, if x is approaching 1 from the right, that means the values for x are 1 plus a little bit. So that means that the values for x are a little greater than 1. Well, when the values for x are equal or greater than 1, the function itself becomes 2x. So we're taking the limit of 2x as x approaches 1 from the right. Again, the limit of the function as x approaches 1 from the right means that the values for x are a little greater than 1. So if the values for x are a little greater than 1, the function becomes 2x. So substituting 1 in for x, we get the limit of 2x as x approaches 1 from the right is equal to 2. So the left and right limits exist, but they are not equal to each other. So the second condition is not met. In order for the ordinary limit to exist, both the left and right limits must exist, which they do, but they must be equal to each other, and they are not equal to each other. So the ordinary limit doesn't exist. So here, condition 2 is not satisfied. If any one of these three conditions are not met, then the function is not continuous at the point x equal to a. So it's not continuous at x equal to 1. It's not continuous. If any one of these three conditions are not satisfied, the function fails to be continuous at that point. So again, we're still looking at the continuity at a point, and we're not looking at the graph at that particular point to determine if the function is continuous. We're using the definition of continuity at that point. Now, in order for a function to be continuous at a point, then all three of these conditions must be satisfied. So we're looking at one last example, and that is f of x is equal to x squared minus 9 over x minus 3, provided that x is not equal to 3. And when x is equal to 3, the function is equal to simply 6. So the first thing to note is that x squared minus 9 over x minus 3 is equal to x plus 3 times x minus 3 all over x minus 3. Now, I can cancel the factor of x minus 3 as long as x is not equal to 3, and it tells you that x is not equal to 3. So x squared minus 9 over x plus 3 simply becomes x plus 3. So the function f of x is actually equal to x plus 3 as long as x is not equal to 3. When x is equal to 3, the function f of x is equal to 6. So the first thing we need to do to determine if it's continuous at a point, and if it fails to be continuous, then it's probably going to fail to be continuous at x equal to 3, because that's where the function starts doing some strange things. So the function f of x is actually equal to x plus 3 as long as x is not equal to 3. Otherwise, or at x equal to 3, the function is equal to 6. So the first thing we have to do to determine if it's continuous at x equal to 3 is find f of a. In this case, f of 3. So we need to know what is the value of the function when x is equal to 3. Well, the value of the function when x equal to 3 is 6. So the first condition is satisfied. The second condition is we have to see if the ordinary limit as x approaches 3 exists. In order to determine if the ordinary limit exists, then we have to look at both the left and right limits. We have to look at the limit of the function as x approaches 3 from the left, and we also have to look at the limit of the function f of x as x approaches 3 from the right. So we need to determine if we're taking the limit of x plus 3 or the limit of 6. Now, if x approaches 3 from the left, that means the values for x are a little less than 3. Well, if they're a little less than 3, that means they're not equal to 3. So we're taking the limit of x plus 3 as x approaches 3 from the left, which would be equal to, plugging 3 in, would be 6. Now remember, this is not a negative. It's not in front of the 3. It's to the right of the 3. So that means the values for 3, the values for x are a little less than 3. 3 take away a little bit. The limit of f of x as x approaches 3 from the right means the values for x are greater than 3. Well, if they're greater than 3, again, they're not equal to 3. So we're evaluating the limit of x plus 3 as x approaches 3 from the right. And plugging 3 in, that gives you 6. So the left limit and the right limit both exist and are equal to each other. So that means that the ordinary limit exists. And the last step is we have to see if the ordinary limit, which we just found, as x approaches 3, is equal to f of a, which is f of 3. Well, we just determined that the ordinary limit does exist and is equal to 6. And in the first step, we determined that f of 3 was also equal to 6. So here, all three conditions are met. So here, the function is continuous. The function is continuous at x equal to 3, because all three of these conditions are satisfied. So that ends our discussion on limits. So instead of assigning you the problems on page 107 like I initially did, you will find a worksheet in Blackboard on limits. So what I want you to do is download that PDF and work the problems out. make sure that you show your work, and then you will send that back to me as a PDF file for me to grade as homework.